Hello and welcome back to TCP and You. My name is Chris Gabrielson, and this is the start of part 3, the common problem scenarios. And within this part, I've put together a few examples to demonstrate some of the more common problems that I see in the field. Specifically, we're going to start off with some intermittent packet loss examples. And with this, I've got an actual use case of a customer who had just a relatively small amount of packet loss, but that small loss had a very big impact on the total performance of their session. And so I'm going to take you through some of these steps that I went through in order to make that analysis so that hopefully you could do the same thing on your end. Then we're going to focus on what does slowness look like when there's no packet loss. And we've actually got two different examples of this. So one is how to validate that all of our settings are good and that our potential theoretical throughput, which we covered in the previous section, how do we know that that's very high, but the systems involved simply don't want to use it? So that's something we'll be looking for. And then in signs of an endpoint issue, we'll be looking for some red flags which might stand out and clearly indicate that one side or the other is having problems. That would be things like window zero sizing and just general gaps in the transmission. So let's go ahead and get started into our intermittent packet loss example. And as I said earlier, this was a real case where a customer migrated from Catalyst 3Ks over to Catalyst 9K switches, and they noticed after the migration, anytime one of their clients tried to download some files from AWS, their Amazon Web Server, the download was significantly slower than expected whenever they used the Cat 9K. If they swapped it out, Cat 9K for 3K, it would work just fine. Or if they swapped it for any other model of Cisco switch or even third-party switches, the speeds would be very good. It was only when the Cat 9K was in use that they started seeing these performance issues. Now, when starting the application, we were able to determine through working with the customer that it would actually kick off two separate TCP sockets that would each get around 350 to 400 megs in the good or working state, and that would give them a collective throughput of just over 700 megs. That's what they were looking for. However, in the broken state, they were getting on average 150 megs across the two streams. So what does our action plan look like for this particular example? Well, as we said at the very beginning of this, slowness is relative. So the first thing that we need to do is get two packet captures from the customer. One needs to be the working or fast capture. The other needs to be the broken or the slow capture. That is key. We must look at the two side by side so we could try to find some anomalies. Then, because these captures were quite large and I want to focus on just a single TCP stream, I filtered out a TCP flow in question. Even though the application started two, I chose just one, and I wanted to focus on just that one. And I did that by going to the statistics drop down menu, then conversations. That creates a new window. In the new window that appears, you go over to the TCP tab and then sort by packets. And I grabbed the largest TCP flow I could find. And then in step 3, I went to the TCP throughput graph first in order to see what's happening in the fast versus slow. And as we talked about in the previous slide, you can get there by going to statistics, then TCP stream graphs, and then throughput graphs in Wireshark. Now once I had that throughput graph side by side, this is what I saw. We could see that the slow capture up top is definitely very different looking from the one on the bottom. And I also would say keep in mind these are different periods of time long. So what we're looking here on the x-axis, this is time 0, this is 25 seconds in, 50, 75, 100, all the way up to just over 175 seconds, whereas our bottom one is 55 seconds. However, despite that, we could see even in the first 50 some odd seconds, there was only really two big drops happening in the fast capture. But when I look at the slower capture, Here at the 25-second mark, there's 3, and right around that 50 to 55-second mark, there's at least another 3 more. And it appears that they are constantly occurring. I could also tell from these two captures my rates are constantly changing. This is a throughput graph, so it tells me I should be able to tell how fast the capture was going. Now, if you look, this sort of slow ramp up start is common to both of them. Here, we were kind of ramping up and it peaked just before 25 seconds. So let's just call this maybe like 15 or 18 seconds. Here, that lasted past the 15 or 18. It went all the way up to about 22, 23. But during that time, the traffic in the fast capture was able to hit and sustain over 350 megs. We call it 360 to maybe 380. That's this line going across. I know that because the throughput is over here on the right. This is 1 times 10 to the 8, 2 times 10 to the 8, 3 times 10 to the 8. So now we just count up the number of little dashes, and that's where I'm estimating it's around this 360 to 380 mark. So we can see there's a good amount of time that it's kind of staying up here. At the very least, even with this one little dip, the vast majority of the time it is over 300 megs per second. Comparing that with the slow capture, the numbers on the y-axis changed a little bit. This is 5 times 10 to the 7. Then I get to 1 times 10 to the 8, 1.5, 2, 2.5. It doesn't even get to 3. So that tells me this peak here, we peaked at around 250 megs a second, but it was extremely short-lived. The vast majority of the time we are between these two faint gray lines. So that is between 5, or rather 0.5 and 1.0 times 10 to the 8. So let's just call it around 75 megs per second. Assuming the other TCP stream also ran at that speed, it would make sense where the customer is getting their 150 megs of throughput. Okay, so definitely something very interesting going on with these captures where, for whatever reason, our throughput suddenly drops. So the next thing I want to do is start looking at packet loss. And the easiest way to tell how often or where the loss might be occurring is through an I/O graph. And we haven't really talked about those in the previous slides, but they are fairly simple. If you go to statistics in Wireshark, in one of the drop downs is something called I/O graph. And when you click that, you're going to get something similar to this graphic. And by default, the all packets checkbox here will usually be selected. I want to deselect that as seen here, and then I want to create a new filter. In this case, I just called it TCP errors. If you double click in this area, you can modify it as you see fit. And what I'm going to do is I'm going to double click in the display filter, and I'm going to apply this filter here, the one in bold, tcp.analysis.retransmission or tcp.analysis.duplicate_ACK. I know both of these, both retransmissions and dup/ACKs, are signs of packet loss. If you see them, then you could pretty much be guaranteed someone on the network is seeing packet loss. And so with this, I can graph them out knowing that there's usually a lot more duplicate ACKs than there are retransmissions. I can graph it out and get a sense of how often and how many there may have been. And you could also see my style here was changed to a bar. Again, just double clicking this, you get a drop down menu. You could change it to like line, F bar, impulse, dot, whatever. There's a bunch of options, but I just went with a bar in order to see it this way. Now, this is in the slow capture. Let's do the same thing in the fast and compare them. When I do that, I get this. Now, I have a little highlight here. There was a key exchange where just one particular key wasn't being accepted, and that's unrelated to TCP, so I ignore it. You actually see the same thing. There's a very tiny little blip here in the slow capture, so that's not something I care about. But if I were to look at these two, there's a good bit of observations we can make. So on the fast capture, we see the largest period of free or non-packet loss, about 35 seconds. We didn't lose a single packet. The fast capture actually had two instances of packet loss, and these were quite large. If we look over here at packets per second, we could see that this was up near 1,000, and the one over here, this was upwards of 15 to maybe 1,700. So even my fast packet capture had retransmissions and duplicate acts, but that's working. Customer doesn't care about that one, so I'm going to essentially discard them. But then let's look at our slow capture. What am I seeing? I have it all called out here. The loss is much more frequent. Here in 55 seconds, I had 2 instances of loss. Here in 55 seconds, I have 7. So over 3 times the amount or the frequency that loss is occurring. I also see over the course of this entire capture, there seems to be little consistency. It's not like once every 10 seconds I'm seeing something or once every 30. It's all over the place. Here we could see these 3 little bars, one stacked on top of another. That's 3 instances of loss, one after the other after the other. Then I have a period of time where nothing happens. Then loss, nothing. Loss, shorter period of time, loss. Here there's a great big area where nothing goes wrong, and then a whole bunch of loss. So really, it's not making a whole lot of sense from a pattern perspective, but I can clearly see the amount of packet loss is changing quite a bit. Okay, well, what does this mean then in terms of some of the other TCP settings that we learned? The next thing I'm going to look at is the window scaling, and because I have the 3-way handshake, I could use the window scale graph in Wireshark to see if anything stands out. And this is what I see. Again, you can get here by going to Statistics, TCP Stream Graph, and then Window Scaling within Wireshark. And make sure in both outputs that you deselect the bytes out. I want to look at only the receive window because that is what is being read from the packets themselves in order to see, okay, what is the client saying is an acceptable window size. And there's a few things, once again, that kind of line up here. So to start, there is a slow ramp up. If you've ever heard of TCP's slow ramp or the slow windowing up, that's happening in both these instances. Remember, the top one is 175 seconds long. The bottom one is 55. Therefore, the top one is a bit more skewed, but essentially these last approximately the same amount of time. If I look at the levels in which they're hitting, so essentially all these packets will create this solid green line. There are some dips here and there, but for the most part, the overwhelming majority of the time, we see that there's this line up top. And in both these cases, it's just over this 3 million value. So that tells me in both the working and the broken state, the receive window size is identical. So this is not a problem of the window size changing in broken and fast. I don't have it here, I did look at the latency. Latency was identical because our client was staying in the same path going out to the same server. The only thing that was changing was the frequency of loss. And it just so happens that if I were to overlay, which is what I have here, the TCP throughput graph and my I/O graph with the retransmission and duplicate ACK bars, and I were to impose them like this. So this is 2 different graphs that I've just lined up, and I also adjusted the size so that the time markers approximately line up. And sure enough, what do you see? I've made it fairly obvious here with the arrows, but every time there is packet loss, even a small amount of loss like what we see here, TCP no longer tries to go up in speed, it goes down. And then if there's a period with no loss, we could see here it tries to recover, and as it's recovering, it gets packet loss, so it goes down. Tries to recover, then it gets packet loss and it goes down. And this continues. If we have a lot of packet loss like we see here, that brings the speed lower and lower and lower until finally TCP is now trying to recover. So far so good. It's got no packet loss. It's going really high. Oh, all of a sudden I get more packet loss. Here we can see there's lots of little bars relatively close together. So what happens from this speed? We bring the speed way down because we're trying to find a happy medium where there's no packet loss. And we start to hit that here and we say, hey, maybe it's time to start speeding up again. We try to speed up and once again we hit loss. Here the loss is just spread enough where it keeps us around this, let's just call it, this is between 5 and 7.5, we'll call it around maybe 60 to 70 megs per second. So what does our final analysis look like? Well, the slow capture that we've been looking at actually contained about 1.1 million TCP packets in the flow. The retransmissions, however, totaled about 239. So 239 packets out of 1.1 million, and that was over about 100, nearly 200 seconds. So a pretty sizable amount of time. But that small amount of retransmissions were able to bring the expected throughput down by over 60%. And what was happening here was that the frequency of the transmissions caused the server to cut back its transmission rate every time they were seen. The client would send a window size update saying, hey, let's bring the window right back up to 3.1 megs. I can handle more data if you're willing to send it to me. But instead, the server chose, in order to conserve bandwidth, the server chose to slow down even though the client was asking for higher speeds. And we would see that the server would take multiple seconds to ramp back up, and if we had any sort of packet loss during that ramp up speed, the server would cut way down and try to find another happy medium. Now in this instance, the latency for this particular location going to that server was between 60 to 70 milliseconds, and this was partially contributing to the ramp up of the server. Part of the mechanism of TCP that we really didn't cover a whole lot in this training was, depending on how many duplicate ACKs is received by a source, that may determine how much it sends as part of the recovery. Meaning, if you have a very high latency environment, let's just say you're going from the US to China, something where you're going halfway around the world, I expect 200 milliseconds of latency. Well, that means if there's packet loss, knowing what we know about those duplicate acknowledgments, there's going to be quite a few if there's a big window size. There's going to be a lot of packets out kind of in transit, and so that means the receiver is going to get probably thousands of duplicate ACKs. As a result, that receiver realizes, hey, there's a lot of latency here, so I better take a really long time to try to recover this TCP session. Versus if this was two PCs that were on a LAN, it might only get one or two duplicate ACKs, assuming that the LAN latency is only a few milliseconds, likely 1 or 2 milliseconds, maybe even less, depending on its size. They could very quickly discover that loss, recover from it, and even though the TCP window might get cut down, it'll recover much more quickly as opposed to something that's going across a higher latency. And this also brings us to our next example, which is slowness with no loss. And this could be sort of tricky. What happens if you go through this entire process and you see that there is still evidence of slowness in the environment, but the customer says, yeah, but there's no packet loss? Well, in that case, it may not be an issue with the network. It might be something with the client. And so for the next couple of slides, we're going to reanalyze parts of this capture to determine what does it mean for a server's congestion window to be playing a role. Remember, the congestion window cannot be seen in a packet capture. It's entirely managed by the endpoint and is often something that needs to be set. The easiest way to visualize this is with our throughput graph, which is the top one here. This is the TCP throughput graph we just looked at, overlaid on our TCP window size graph. Now, what exactly are we looking at here? Well, we could see that in the TCP window size graph, within, let's just call this the 12-second mark. I've tried to align my timestamps here, so it's 10 seconds, 10 seconds. Within, let's just call it 12 seconds, 11 to 12 seconds, the window size hits this maximum value and pretty much stays there the entire time. Now, once we, at this 11-second mark, once we hit this 3.1 megs, if we were to use one of those calculators that we learned about earlier, with, let's just call it 65 to 67 milliseconds of latency on a 1 gig link with a 3.1 meg window size, technically, this TCP connection has a maximum theoretical throughput of around 370 to 380 megs. So right here at the 11-second mark, this server could be transmitting 380 megs a second. But instead, it's way down here. We're probably only doing, what is this, maybe 50 megs a second? And we can see the server is taking a very long time, multiple seconds. This goes from, let's just call it 11 to maybe 21. It takes nearly 10 seconds of loss-free data transmission before it's comfortable in order to start sending at this high line rate. This block right here is evidence of the server windowing up. It's part of its congestion window where it's looking for a certain period of time where there's no packet loss, and if there's no packet loss, it will start putting more packets on the wire. But it is not obligated to do so by the client's receive window that it's being sent. So this right here, this is not a network problem. This is entirely a setting on the server. We could see then the server is doing great. It's transmitting a whole bunch of data. And then if you remember from the previous slides, this is the first instance where we had packet loss. And so what happens? The server says, oh, there was some packet loss. Let me back off. I'm going to slow the speed down a little bit. And then I'm going to recover whenever I am ready. And if we look, it's a little hard to see, but essentially the window size, there's you can kind of see it here right where my mouse is. The window size dropped down quite a bit from the client because the client could detect the packet loss as well. But then it recovered within a millisecond. We're almost right back up. We're definitely over the 3 meg mark, but for the most part, we're at the 3.1. So we're pretty much back in terms of that window speed or window size, but the throughput of the server takes about another 10 seconds before it's comfortable going back at line rate. So this right here, this is evidence of the server's congestion window, as is this to an extent. We could see that this was our second instance of packet loss. There was a big drop, and so the server, because of the amount of loss, dropped much further down and slowly started to recover. But then we could see that here the client started adjusting the window size. In this instance, based on our I/O graph from earlier, there was no packet loss. This is strictly the client adjusting the window size, and the server is adjusting its throughput accordingly. Now, how is it that we could test whether or not this is something that we can modify? Because I've talked about how difficult some of these issues could be. And one of the tools that I actually like is iPerf. Sometimes if you've worked with customers in iPerf in the past, it could be a real pain in order to determine whether or not maybe you have an iPerf issue, a PC issue, or something else. So when dealing with iPerf, and if you're unfamiliar with iPerf, you can go to iperf.fr, I believe, and it's a simple command line tool. I believe it works on both Mac and PC. You could see here is my PC. And you simply navigate to the iperf.exe. -C is client. And here I'm using a public iPerf server hosted by Hurricane Electric. That's he.net. And all I'm doing, I did this from one of the Cisco offices. So I'm not using a VPN. That's very important. But I'm in the Cisco office here. And all I did was change the window size and run this test with the default settings. Because again, this goes back to calculating our maximum theoretical throughput for TCP. Remember from, I believe it was part 2, if we have a window size of 1460 bytes, which is one packet, and 1,000 milliseconds of round trip latency, what's the maximum theoretical throughput? Well, it was 1460 bytes per second. Even with no packet loss, that is as fast as the connection could go. That's all the result of this window size. And so here you could see I tried 3 different window sizes. I started off with a window size of 100,000 bytes, and I kept it there. That was the max. Then I increased it to 1 meg. Then I increased it to 5 megs. And just by modifying the window size, nothing else changed. My latency stayed the same. The server I was connecting to stayed the same. Everything else remained constant, yet I got 3 completely different speeds. With a window size of 100,000 bytes, I could only transmit 15.4 megabits per second. As soon as I bumped it up to 1 meg, I got 120 megs per second. When I bumped it up to 5 megs, now I got 566 megabits per second. So this is a very good way to maybe visualize whether or not we have a network or client issue. And I like to use iPerf in a customer's network because a lot of times they might say, hey, I've got speed test is failing, or I think this is a network problem or something else. And I could set up iPerf between 2 devices and show them that simply by modifying some of the window sizes, they could be putting arbitrary limits in terms of how fast the connection can go. And by bumping it up to usually around 5 or 6, usually no more than 8, because that's about as fast as you can go for most gig links. But once I get up to 5 megs, I could very quickly get some pretty impressive speeds on a single gig interface. So keep in mind this might be a tool that you want to put in your arsenal in order to help with your troubleshooting and to demonstrate to a customer that there are some settings which are completely managed by the server and client and have nothing to do with the network. This is also something where if you know how to calculate your throughput for TCP and you don't see any packet loss on the network, it might be a sign that maybe the window size is at play or we're dealing with the server's congestion window, at which point usually the lack of packet loss and other evidence is a sign that that's something that they need to handle with the server admins. Okay, almost done, approaching the very last slide, and this is going to be just a quick slowness with no loss example, and I want to briefly talk about the TCP window size 0. And this is where if we have a client that is being overwhelmed with data and you apply the filter tcp.analysis.0_window, you may see something like this. We see TCP 0 window, and if I look at the window size here, again, this is something where you need to have the 3-way handshake for kind of the best result, but looking at the window size equals 0, right, win equals 0, this is how the client is able to tell the destination, stop sending me data. The window size is now 0. I can't handle anymore. Well, what's an example of how or why this would happen? Think about an old PC. Maybe it's got an internal hard drive that is a spinning disk. We are limited in terms of how much data we could write to that disk per second. Let's pretend my write speed to that disk is 100 megabits per second, but my PC has a 1 gig connection to the network. This means the network could theoretically send data 10 times faster than we can save it. And eventually, if we get too much data, we're going to run out of memory or run out of temporary storage before it could all be written to the hard drive. As a result, the client needs some way of telling the destination, slow down, I'm still trying to process all the data you just sent me, and this is the way we do it. And we can see here I have highlighted the milliseconds since the first TCP0 window and the last one here. And it's over 500 milliseconds, which in the case of networking is a tremendous amount of time. We can see the client is setting this zero window, but it's also constantly acknowledging a lot of the data that it receives. So at ACT, about 200,000 bytes of data here, and then at the end, acknowledged about 3.4 million bytes of data. So it was still receiving data, it's getting all this data, but it was telling the destination, stop sending me more, and it was just processing what was already in flight. And 500 milliseconds worth of zero window, that will slow down a TCP transfer quite considerably. Going back to our example, right? Imagine your round trip time is 500 milliseconds instead of the 1000 millisecond example when we were calculating potential throughput. Same thing here, right? One side is not sending anything. So if you see zero window, that's an indication your client is being overwhelmed. Otherwise, if you don't see this, you don't see retransmissions, you don't see duplicate acts, you see no signs of packet loss whatsoever, and you see a window size that is very large and has the ability to send a lot more data than what's there, then that is a sign we are dealing with the congestion window of the server, and it is not a network problem. I hope that helped to clarify some things. Up next in part 4, we're going to go over some quick tips and tricks for troubleshooting these things and hopefully giving you some tools to make a quick analysis and show a customer whether or not the network may or may not be at fault.